18 light years, in cosmic terms, practically next door. For comparison, the light you see from this star tonight left it in the year 2007, when the first iPhone was announced, when nobody knew what a smartphone was. The star is called GJ251, a red dwarf, unremarkable, dim, one of billions, the kind of star you find in catalogs, but not in textbooks. Since 2019, scientists knew this star had a planet, a super-Earth, too close to the star for life. Interesting, but not remarkable. The observations were archived, the telescopes moved on. But hidden in that data lay something else, a signal so faint it went unnoticed for years. A second world, a planet orbiting exactly where liquid water could exist. 18 light years away, the whole time. This is the story of what we almost overlooked. To understand how you miss a planet practically on your doorstep, you need to understand how we search for planets at all. The radial velocity method. When a planet orbits a star, its gravity tugs on that star. The star wobbles. Not much, sometimes just meters per second, but enough that the star's light shifts slightly. Red when it moves away from us, blue when it approaches. Penn State University built an instrument specifically for this, the Habitable Zone Planet Finder, HPF, mounted on the Habitable Telescope in Texas, designed to measure the infrared light from nearby stars with highest precision. Their goal, to find worlds where liquid water could exist. The Goldilocks zone, not too hot, not too cold. GJ251 had been on the observation list for 20 years. Data from the HARPS instrument in Chile, from the ESPRESSO spectrograph in Paranal, from the NEID spectrometer at Kitt Peak Observatory, hundreds of nights, thousands of measurements. 2019, the first signal, a planet with a 14-day orbit, GJ251b, 3.85 Earth masses, but far too close to the star, surface temperature several hundred degrees. The discovery was published, archived, checked off, but in the data lay something else, a fainter pattern, a longer period, 54 days. The problem: stars have weather, magnetic activity, star spots. All of this creates signals that can look like planets, false positives, ghosts in the data. How do you distinguish a planetary signal from stellar noise? You wait, you collect more data, you develop better algorithms. For 20 years, Corey Beard, doctoral candidate at the University of California, Irvine, his dissertation, The Search for Low-Mass Worlds Nearby That Could Be Candidates for Direct Imaging. GJ251 was perfect. Close. Known planet, 20 years of data. But the data was chaos. Stellar activity overlaid everything, like trying to hear a whisper in a storm. The team applied what Suvroth Mahadevan, professor at Penn State, describes as a hard game. They analyzed how signals change across different wavelengths, different colors of light. Planetary signals are wavelength independent. Stellar activity is not. For months, the team worked through the data. The known 14-day period of GJ251b was their baseline, their reference point. Then, slowly, the second signal emerged. 54 days, consistent across 20 years, consistent across all wavelengths, not stellar activity, a planet. GJ251c. Mass 3.8, 4 times Earth. At minimum, probably rocky, a super-Earth. Orbital distance, 0.5 astronomical units, about half the distance from Earth to the Sun. But GJ251 is not a sun-like star. It's a red dwarf. Cooler, dimmer. The habitable zone lies much closer. 54-day orbit, right in the Goldilocks zone. Publication came in October 2025. The Astronomical Journal, title, Discovery of a Nearby Habitable Zone Super-Earth Candidate, Amenable to Direct Imaging.
Amenable to direct imaging.
That's the key phrase. That's what separates this planet from thousands of others. We could see it, not just its wobble in starlight, but itself, its own light, its atmosphere, if it has one. Directly imaging an exoplanet is incredibly difficult. Imagine trying to photograph a firefly sitting next to a spotlight from 1,000 kilometers away. The firefly is the planet, the spotlight is the star. The star's light is millions of times brighter than the planet's reflected light. So far, we've only been able to directly image a handful of planets, mostly young gas giants still glowing from their formation heat, or planets on extremely wide orbits where starlight is weaker. The most famous example, HR 8799, 4 gas giants directly imaged by the James Webb Space Telescope, but these planets are massive and far from their star. GJ251c is different. a rocky world, close to its star, cool enough for liquid water. The James Webb Space Telescope cannot image it, too close to the star, too faint. But the next generation of telescopes might succeed. The 30-meter telescope, the giant Magellan Telescope, the European Southern Observatory's extremely large telescope, all in the 30-meter class, all with adaptive optics that correct atmospheric distortions. And in the 2040s, the Habitable Worlds Observatory, a NASA mission specifically designed to characterize Earth-like planets in habitable zones. Corey Beard, in the publication, "We are at the cutting edge of technology and analysis methods with this system. We need the next generation of telescopes to directly image this candidate. But what we also need is community investment." Community investment, a polite academic term for we need money, political will, public interest. Because here's the truth. The telescopes that could image GJ251c don't exist yet. Some are under construction, some are planned, some are just concepts on paper. The next 5 to 10 years will determine whether we ever see this planet's atmosphere, or whether it joins the forgotten discoveries. Let's talk about what we're actually searching for. An atmosphere, not just any atmosphere, one with biosignatures, chemical markers indicating life, oxygen, methane, ozone, in specific combinations that are difficult to explain without biological processes. If we can directly image the light from GJ251c, we can break it into its colors, a spectrum. Every molecule in the atmosphere absorbs specific wavelengths, leaves fingerprints in the light. The Armazone's high dispersion, a shell spectrograph, and DS at ESO's Very Large Telescope is being built exactly for this, to search for biosignatures in Earth-like planets. The Habitable Worlds Observatory will go even further. But here's the realization nobody likes. These instruments might find nothing. GJ251c might have no atmosphere. Red dwarfs are active stars, flares, magnetic storms. In their youth, they might have blown away the atmospheres of close planets. Or the planet might have an atmosphere, but no biosignatures. A Venus, a Mars, cold and dead, or hot and toxic. Or, and this is the most unsettling, it could be perfect. Liquid water, a stable atmosphere, but no life. Just chemistry, just physics. No biology. Suvrath Mahadevan, in an interview, this represents one of the best candidates in the search for atmospheric signatures of life elsewhere in the next 5 to 10 years. One of the best candidates, not a guarantee, a candidate. But here's what this discovery really means. We have a planet 18 light years away that we can study in our lifetime, with technology already being developed. TRAPPIST-1 is over 40 light years away. Proxima Centauri b is 4 light years away, but orbits an even more active star. GJ251c is the sweet spot, close enough, quiet enough, bright enough. If we're going to find a second Earth anywhere, this is one of the best places to look. Over 7,000 exoplanets are confirmed. Estimates suggest billions more in our galaxy. Most will never have names, most will never be studied, most will be forgotten as soon as they're discovered. GJ251c was almost forgotten too. The signal was in the data for 20 years, unnoticed, overlooked. How many other worlds are hiding in our archives, in data already collected but not yet analyzed? The next generation of telescopes won't just find new planets, they'll revisit the old ones, the overlooked, the forgotten. Perhaps that's the real lesson. The most important discoveries don't always lie ahead. Sometimes they lie behind us, in data we already have, in signals we haven't yet understood. 18 light years, practically next door. There the whole time, waiting 20 years of data, one overlooked signal. A second Earth could be 18 light years away.